Ahmed Hatami, Noam Lifshitz, Sarah Peluz, Jacob Fox, and Shakar Lovett for their work in putting together a great program. Go ahead and clap for our program organizers. I like that. Thank you. So these are just a couple of logistics for this week. So food is provided before the first talk, so just now, and then during the breaks. But lunch, you're on your own, and there are some great places, of course, to eat, right? Like everywhere around here within a 3-minute walk, really. Let's see, what else? We ask that you always leave food outside the room. We don't bring any food in here. There are lockers on the far side of the building on the first floor. If you want to leave your things during lunch break, for example, don't leave your things unattended. It's Berkeley, our campuses, all campuses, but just don't do it. Our videographer, Omid Far, will be helping speakers get set up for talks, and Omid's in his professional booth over there. Finally, I would like to give a special thanks. You may see them popping in and out. Elizabeth and Ashley from the Simons Institute events team for managing all the logistics for this week, including accommodations for our out-of-town visitors. And now I'm going to hand things over to Hamid. Is that right? Yeah. Who will say a few more words about the workshop. Thanks. That's somebody's name?
Yeah, there's free transfer. Okay. So welcome everybody. I'm glad that many of you made it and could come to this workshop. So one small thing I want to say is that the talks most of the talks are 1 hour, and there's a lot of talks every day, 4 hours, 4 talks for most of the days. And so some feedback we got from the previous workshop is that you don't have to really go all the way, use all your 1 hour. I mean, you can if you want, but you can leave 10 minutes for questions or discussions if you don't have enough material to say, like, don't feel pressure to use all the 1 hour. And yeah, other than that, I'll just have Yufei at the workshop.
All right, thank you. It's a great pleasure and honor to give the first talk of this workshop. So I'll tell you about our work on KSAT, and the title and also the statement of main theorem is that nearly all KSAT functions are unate. Can you see the pen, or should I try a different? Okay. If you want me to switch a pen, just let me know. Okay, so nearly all KSAT functions are unate, and this is joint work with József Balogh, Dingding Dong was my grad student at Harvard. Bernard Lidický and Nitya Mani. So Nitya is also my grad student. Okay. So the basic question here So the basic question here is, how many KSAT functions are there on n variables? Thank you. In this talk, I'm primarily going to think of k as fixed and n going to infinity. But I'll comment on what happens when k is increasing at some point in the talk. So, thank you. Lots of pens. Okay. So just to clarify the notation and the setup, so what I mean by a KSAT function is a Boolean function from n Boolean variables to one output Boolean variable that has a certain form. For concreteness, we're going to work with DNFs, the disjunctive normal form. So for example, a 3-sat would be something like a function taking in n input Boolean variables and having some formula which consists of various clauses, each clause being the end of three literals that could be positive or negated literals, and then or of another clause, and so on and so forth. So that's an example of a three set. So this is a DNF, but equivalently, you can also consider CNFs. So this is an OR of ends, a CNF or ends of ORs. For the purpose of counting functions, the negation of a DNF is a CNF and vice versa. So for the purpose of counting these functions, it doesn't matter which form you use.
The K bounds how many conjuncts in each disjunct?
That's right. So this is K equals to 3. Yeah, so each clause, the width of each clause is K.
Okay. But you could have like a million disjuncts.
That's right. I do not restrict the number of clauses. Please ask. So how many K-sat functions are there on n variables? And also, what does a typical one look like? So let me first clarify a confusion people often have when they hear about this problem, which is that this is not about whether a random K-sat formula is satisfiable. Right? So that's a different line of work, also very important, and for which there's some important breakthroughs, namely the solution of the satisfiability conjecture. This is not about that. Right? So this is about K-sat functions. Okay, so
the distribution is really uniform over all possible functions expressible as K-sat.
That's right. Yeah. So take all functions expressible as K-sat, and that's what the typical structure of such a function is like.
So it's most one of them not described.
But there will be other formulations you'll see later. So let's first give some easy upper bounds. The total number of functions from n variables to one output variable is 2 to the 2 to the n. So that's an upper bound. The number of K-sat clauses, well, you have 2n possible literals to put in each position and k different positions. So let me write down this bound, 2n to the k. So then the number of K-sat functions is 2 to this quantity because I can include each such clause or not. So already for a fixed k and large n, you see that the number of K-sat functions is a tiny fraction of number of total functions. Let me also explain some lower bound constructions. We can consider monotone functions. So monotone functions is a function that can be expressed using a formula involving only positive literals. So xi, but we do not use xi bar. Okay, so we do not use xi bar. So these are monotone functions. The number of monotone functions is, well, n choose k possible clauses and 2 to n choose k. So that's the number of monotone functions. Here, there's a small caveat I'm assuming that all the clauses have distinct variables, but let's not worry about that. Unate means that the formula or the function is monotone after first negating a subset of variables. So for example, you start with a monotone formula, And then you say that I'm going to negate all the instances of x2 and negate all the instances of x5. So that would be an example of a unate function. The number of unate functions is also not too hard to estimate. Basically, you give me a monotone function and a choice of which variables to negate. There's a bit of overcounting here because a formula might not use all the variables, but that represents a negligibly small fraction of all functions, so let me not worry too much about it. So it's up to 1 plus little 1 error, this quantity here. The number of unate functions is that quantity. So this problem was first studied systematically in the paper by Bollobás, Brightwell, and Lidický. And they conjectured that for a fixed k, the number of k-sat functions on n variables is this quantity here, coinciding with the asymptotics of the number of unate functions. So an equivalent formulation of this conjecture is that 1 minus little 1 fraction of all k-sat functions are unate. Let me say a few words about the history of this conjecture. So this paper by Bollobás, Brightwell, and Lidický, they proved a weaker version of the conjecture for k equals to 2, showing that the number of 2-sat functions is 2 to the 1 plus little 1 and choose 2. So so it's a weaker asymptotic because 1 plus little 1 is in the exponent. Peter Allen proved it for k equals to 2 in 2007. And then Lidický and Kang in 2012 proved it for k equals to 3. And in our work, we proved this conjecture for all k. It has two parts. So the first part is a paper with my students, Dingding and Nitya. We proved that for all k, this problem can be reduced to a conjecture which has the form of a hypergraph like Turon problem. So I presented this work at a workshop, which then got some people interested. And then together with, additionally with Bernard Lidický and József Balogh, we managed to solve this Turon problem. And this proves the conjecture. So I want to tell you about this work and the ideas in this proof. So this is the problem about asymptotic enumeration. Right? So the statement can be phrased in terms of typical structure, but what we're really doing is finding some upper bound to the number of k-sat functions. And there's a rich history of asymptotic enumeration in graph theory and in combinatorics. And I think that analogy is incredibly useful when we were thinking about this problem, and also a good way for me to explain some of the key ideas. So let me first revisit some of the history and key ideas on combinatorial asymptotic enumeration. And here the motivating question is, how many triangle-free graphs are there on n vertices? This is a great problem. Yeah, so this problem was solved in the 70s by Erdős, Kleitman, and Rothschild. But just because it was solved, people still kept thinking about it. And through it came up with a lot of wonderful combinatorics, including some of the most exciting results in the past decade in combinatorics. So I want to explain a brief history of what are some of the ideas around this problem, and also explain what this has to do with that. Because right now they look kind of different, but I want to relate these two problems to each other. Just to give a very quick history of things that are relevant. So an old result in extremal graph theory, Mentel's theorem and later Turon's theorem, tells us that every n vertex a triangle-free graph has at most n squared over 4 edges. And this is tight because of the complete bipartite graph example. And this work of Erdős, Kleitman, and Rothschild '73. So they show two. They did a lot of things in this paper. But let me first phrase the answer to this question in a slightly weaker way, which is that the number of triangle-free graphs on n vertices is 2 to the 1 plus little 1 n squared over 4 in the exponent. And this is sharp because if you start with a complete bipartite graph, then every subgraph is also triangle-free, and which is you get this number. They showed a stronger result that 1 minus little 1 fraction of all n vertex triangle-free graphs are bipartite. Okay. So this is a much stronger result.
Is it on n-labeled vertices or unlabeled?
Yes, the question is whether it's on n-labeled vertices or unlabeled vertices. It turns out in this case, it doesn't matter because that contributes to a much smaller term.
Does this imply the Bollobás result? Like the bounds are similar?
Okay, you're asking how is this related to that? Okay, so not yet, right? But certainly you see the analogy. So there's an analogy. So let me say a little bit about the techniques and how these things are related to each other on this board. I would say that the paper of Erdős, Kleitman, and Rothschild, it's a pretty short paper. The techniques are a little bit ad hoc. And later work has clarified some unifying techniques for this type of problems. In particular, the regularity method allows you to prove this bound by a standard application of regularity. And more recently, the hypergraph container method. I'll write this down because it will play an important role in this talk. The hypergraph container method So this is an important breakthrough about 10 years ago, separately due to Balogh, Morris-Semoti, and Saxton Thomason. It's an important advance in combinatorics that gives a very powerful method for handling problems such as this one. And by assuming a powerful theorem, one can quickly deduce this part A. To deduce part B, you need to do some more work that's more bespoke to the problem that you're looking at, but essentially a stability type result. Okay, so, and largely, I will ignore this part from the story that I will tell today. It is quite more technical and will distract from my main message. So the hypergraph container method, let me, since I think not everybody here is from the combinatorics community, so let me give a very quick sketch of what the main idea in applying the hypergraph container method is, because it will inform us how to think about the KSAT problem. Here's a sketch of applying containers to the problem of counting triangle-free graphs. So there's some theorem, which is a container theorem, and by applying it to this problem, we get a collection of what are called containers, where each container is a n-vertex graph. Okay. And okay, so each container has a small number of edges, so slightly over the threshold in Mentel's theorem, just a little bit over the number of edges in Mentel's theorem. And also, there are not too many containers. Okay, so the total number of graphs is n to the on the order of n squared. So there's not too many containers. And importantly, and the reason why they're called containers is that every triangle-free graph on n vertices is a subgraph of some container. And once you have a collection of containers with this property, which is what the powerful container theorem can get you, then you can deduce that the number of triangle-free graphs is at most, well, I sum over all containers, G, and for each container, I look at all its possible subgraphs. And I know that this counts all triangle-free graphs because every graph falls in some container. Well, the number of containers is 2 to the little o n squared. And the number of edges in each container is bounded by this quantity here. And together, this gives me the first result. Okay. There's a lot of stuff happening in deducing the existence of this collection, but once you have it, you can quickly deduce the result. And another way to kind of say morally what's going on is the container theorem gives you a very efficient way to do union bounds in a particular setting that has to do with avoiding triangles. Now, in applying this container method, what one often has to do in a typical application is to solve, we need to solve some, identify and solve some extremal problem. Maybe there was this Mentel's theorem, which is related to this quantity here. Okay, so there's some problem that you need to solve like that. And then one also needs to do something called supersaturation, which for dense problems basically comes for free. And for the problems that we're dealing with here, where we're looking at a positive density fraction of edges, it always comes for free. So let's not worry about that today, but in many important applications of container method, supersaturation is a key bottleneck. Okay. Great, I hope this is a clear explanation of how to count triangle-free graphs. And then what I want to explain next is how this has to do with the problem that we started talking about, namely counting KSAT functions, which seems to be a different kind of object. So what do they have to do with each other? but it doesn't generalize as nicely to hypergraph quantitative calculus. Okay, yeah, so there's also the regularity method, which can do many of same things. And a couple of things. One is that it's a lot more difficult to apply the regularity method, especially for higher uniformity or larger K. And also it gives worse bounds, especially when you want to consider sparser objects. Okay. So I want to explain how to view the problem of enumerating K-stat functions through the lens of avoiding forbidden subgraphs. So let's talk about counting K-stat functions. The number of K-stat functions every function has a formula. It may have more than one, but it certainly has at least one. And you can also consider a formula that is minimal in the sense that no clause is redundant, right? What do I mean by minimal? You take a formula, maybe if you delete a clause, nothing changes about the function. Then I just delete that clause. So every function has at least one representative as a minimal K-stat formula. It might have more than one. Actually, it turns out a corollary of our result is that most or almost all have a unique minimal formula. That will be a corollary of the theorem. Okay, but for now, this is an inequality. Now, this formula can be quite complicated. And it turns out that we can focus on a class of formula, which we'll call simple minimal K-stat formula. Simple here as in simple graphs. What I mean is that no two clauses use the exact same set of K variables. So for example, if you have both XYZ and XYZ bar, that's not allowed. It turns out you can rule out non-simple formulas. They don't occupy so much space, and let's focus on the simple ones. I want you to imagine a simple formula as basically a K-uniform hypergraph with some decorations on the edges. Right? You start with n variables, and we put edges, K-uniform edges among these variables, and they have some additional information about which variables are negated or not, but it essentially looks like a K-uniform hypergraph. But there are some forbidden structures in this K-uniform hypergraph, namely those that correspond to non-minimality. For example, this K2-stat formula. Okay, so remember this. If this is an and the commas mean or. So this is non-minimal. It's non-minimal because it's not possible to only satisfy the first clause. You can try, right? So you can try setting in values, and then you'll eventually satisfy something else. It's not possible to only satisfy this one. So this is non-minimal. And you should view this as some kind of a forbidden subgraph. Now, there are lots and lots of forbidden configurations. There are infinitely many forbidden configurations. But what one should do is zone in, fix a special set of forbidden configurations. So number of simple KSAT formula, but now no longer necessarily minimal, but avoiding a prefixed set of non-minimal subformula. Take some space, a finite set of forbidden configurations, as I'm just not going to allow them. And instead of considering minimal ones, I'm going to consider formula avoiding this set of subconfigurations, subformula. Okay. Any questions so far?
Yeah. Is there reason to believe, like a priori, that restricting to finite set of subformulas will give a tight enough bound?
So the question is there reason to believe that it's enough to forbid a finite set? Now, that's a great question, and a priori, no. Right? So it turns out, yes, but a priori, absolutely not. Okay.
Maybe something in that direction. For graphs, forbidding the chromatic number examples
So for hypergraphs, things can get really
very different.
Yeah. So what we will do is show that a typical minimal KSAT formula is in fact unate. And we'll do this via a container counting strategy. So here's a container strategy. It's supposed to mirror what happened for counting triangle-free graphs, but it's actually more complicated. And it's because when you apply the container method to count triangle-free graphs, you end up with an extremal problem, which is about triangle-free graphs. When we're trying to count minimal KSAT formula, or these ones that avoid some fixed set of non-minimal subformula, we, through our analysis, get some extremal problem. But now this problem lives inside a more complicated space. And I want to explain, what is that more complicated space? So containers, what are containers in this case? So this is now kind of viewing it from hindsight. So it turns out the right containers, well, they are KSAT formula, but of a certain special kind. KSAT formula that happen to be semi-simple. So I want to explain what we mean by semi-simple. So simple formula are ones where, if you think about the hypergraph, there are no double edges. So semi-simple means that so compared to a simple graph, so simple formula, we allow up to 2 clauses on every set of k variables. So every k variables support at most 2 clauses. And if they support 2, then the 2 clauses differ by negation on exactly 1 variable. Here's an example. In this formula, I would allow these two, so x, y, x not y, z, and x not y, not z, to both be present because they differ on exactly z. But this would not be allowed. Not allowed. the definition of semi-simple. So it's a little bit more than simple, but we allow some double edges, but double edges have to be of a specific type. Okay, so containers, they turn out to be semi-simple formula. So this is why I say it's in a way more complicated than what happens for the problem of counting triangle free graphs, because somehow when you go through this machinery, you end up with a more complicated space of objects to consider, which I think is interesting. So it's interesting that this happens. And I would say that this is not a limitation of our method. It's an essential feature of the problem. Now, I would say that the main insight, or one of the main insights from our first work in this reducing the problem to a hypergraph container method, or to a hypergraph two-round problem, is in distilling what exactly is the right structure to study and distilling what might be the minimal, non-minimal subformula to forbid. Already here, you can go through the container machinery and come up with some extremal problem, but it's going to have a lot of forbidden structures that's maybe too unwieldy to analyze. And so an insight here is to forget some non-essential structures. And we're going to forget some things and convert these things to what we call partially directed hypergraphs. So it's best to explain this through an example. Suppose I have 4 variables. So it's n equals to 4 and k equals to 3. Consider a formula with some number of clauses. And I want to convert such a formula into some partially directed 3 graph. If I see some clause x, y, z bar, I'm going to put an edge on x, y, z. Hypergraph is going to put an edge, and I will forget about some of the negation structures. If I see a semi-simple edge, x, y, z, x, y bar, x, y, w, x, y bar, like that. Okay, so this is a semi-simple clause. They differ on exactly why. I'm going to convert that to a directed edge. So the directed edge will be on x, y, w with a point directed towards y. So here a direction means the selected vertex. So I point the edge towards a vertex. And that vertex is chosen according to which variable you have the negated difference. Okay, so this is a conversion from semi-simple formula to these objects, partially directed hypergraphs.
That's a question.
Yeah.
These 2 clauses, right? X, Y, W naught, and X, Y bar. We just equivalently identify them as a single 2 clause. But so is there a reason not to do that? Why do you want to remember that?
Yeah, so it gets to a very subtle point, which I think may be better to discuss offline, which is that these things are not, we're trying to count simple minimal formula. And these things arise through, because we're looking at containers. So it's not about counting these guys. We don't actually care about counting semi-simple formula. We care about the structure of the containers. This is it's a fine point. I only care about counting simple formula, but we have to analyze these semi-simple formula because of the method. Okay, so there are some forbidden configurations, and let me give you one example of forbidden configuration. In the case of 2-step. And the forbidden configuration is this partially directed triangle. The triangle with a partially directed edge. With a directed edge. It turns out this is forbidden. Okay, and let me kind of say informally, in what sense is this forbidden? In that if you have a structure which corresponds to and converts to this subgraph, then its to blow up will contain a simple non-minimal subformula. So there's some subtlety to it, but maybe the thing to remember is that these things cause you problems. Okay, so if you have these things in the container, then they will cause you problems. And so they turn out to be forbidden. Okay. Now, we have this collection of containers, not so many containers because of the container theorem. And the number of simple subformula of some container is equal to, well, for each undirected edge, I can either pick the class or not. So 2 to the number of undirected edges. And then 3 to the number of directed edges. Directed edge, then I can either not choose a class from here or choose one of the two to get my simple subformula. And then the extremal problem is to show that this quantity here is no more than what we're trying to prove for the total number of K-SAT formula. And because we have a small number of containers, summing over all the containers would get us basically the result, or the slightly weaker result asymptotically.
I don't understand. So what is the extremal problem?
So if you have a container where this exponent is too large, then I don't have a bound. But if all the containers have that this quantity is at most that, so the extremal problem is to show this. If this is true for every container, right, I want this true for every container, then I'm in good shape.
And what's the bound on the number of containers?
So the bound on the number of containers is it's small. There are more precise bounds, but it's not. Okay. This is all in the k equals 2 case, but you'll see that basically the same story turned out to hold in general.
And do you know that your set of prefixed finite set are they on some number of variables depend on k?
You'll see. I'll tell you exactly what it is. Okay, great. All great questions.
So on the surface, it's like an exponential problem, but really it's a linear question of the types of edges because you take log of this.
That's right. Yeah. So it's a two-round type problem about edge density. So I'll state exactly what the result, what the problem in the result is. Another question that nobody asked, but maybe I preempted it, is that this gives you the weaker result of having asymptotics in the exponent. If you want a stronger result, there are actually quite technical but additional arguments. Lidický and Kong worked out a lot of that argument, and then we can adapt it to the K-SAT case. So there's some very technical arguments that essentially stability type arguments allow you to get from here to a much tighter result.
So do this first as like a rough count, and then you have like that.
Yeah, so I mean, the way these stability arguments usually work is that you say if you're very far from your desired configuration, then you have that rough bound. If you're very close, then you have much more control over the actual structure, close to Unate. And then
Yeah. Oh, I see. Of course. Yeah.
How bad is the little of one, the constant in these kind of statements?
How bad is the dependence? We haven't worked it out, but we're using invoking theorems, container theorems, have some dependencies.
But I'm saying these stability results to get the 1% low of one.
They're all polynomial type.
Okay.
So you're just talking about right now, just the application of the containers there.
That's right. That's right. Okay. So now, in the last part of the talk, I want to tell you what is the extremal problem, more precisely, and what is the result of the extremal problem. So let's talk about the extremal problem. So here is a typical theorem, again, continuing what happens for 2SAT. We will write throughout alpha to be the density of undirected edges. Total number divided by n choose k, and then beta to be the density of directed edges. So here's something that we know is true. In a 2 PDG, so partially directed graph, that avoids this configuration. Okay, so in a 2 PDG that avoids this configuration. And by the way, another technical point is that by avoiding this, I mean also any further directions. Like for example, that is also forbidden. If I avoid this, then that is also forbidden. So not dwell too much on that. Okay, so in a 2 PDG that avoids this forbidden configuration, we have alpha plus 2 beta is at most 1 plus little 1. Okay, so this is some Turon type result. If you forbid some configuration, then some weighted edge count is at most something. This 2 turns out to be tight. Actually, both numbers turn out to be tight. And the example is either you have a complete set of undirected edges or all directed edges from one half to another half. And furthermore, this result through all of that framework would imply the main conjecture for 2SAT. Basically because of everything I said and hand waved earlier. So this is the extremal problem that was discussed earlier. That result implies that, well, what we hear is that this 2, okay, so this implies in particular alpha plus log base 2 of 3, beta is at most 1 plus little 1, because 2 is bigger than log base 2 of 3. And if you take log 2 of both sides, then that inequality is this inequality that we want to show. All right. What happens then for larger values of k? I mean, spell it out for what happens for 3SAT. Just that in a 3SAT, 3 PDG, that avoids some particular structure. And let me tell you exactly what structure is. It's a generalization of this directed triangle where I add a common vertex to all 3 edges. Still has 3 edges, but I add a common vertex to all 3 edges. So you start with this as a 2 PDG and add 1 vertex that's common to everything. Forbid that structure, then we still get alpha plus log base 2 of 3, beta is at most 1 plus little 1. That turns out to be true. Although in this case, we do not know what is the optimal constant here, but for the purpose of the K-SAT conjecture, this is true. And it would then also imply BBL conjecture for 3SAT. Okay. And more generally, for K-SAT, what I would do is replace the thing in the middle by K minus 2 vertices, so that this is a structure that is forbidden. And okay, then we end up having that. Okay. So in a way, this is okay. So this is the content of the second paper. As I mentioned, there were 2 parts. So let me just say a quick word about how we ended up proving that. Now, the short answer is that we used the method of flag algebras. Now, what that is essentially is a sum of squares proof. So we managed to find some sum of squares certificate to solve this problem. You see that we have to do it for every k, so it's not simply some numerical output. We have to give a formula, but it was actually pretty essential that we used computer help to guide us, because there's too many possibilities, right? To guide us to find the pattern and then we can write down a very short certificate. So let me just, it's a very short certificate. Let me now write it down for you. So it's takes a page to verify, right? It doesn't take a computer to verify. You can verify in the page, but it's a very short certificate. So that's in a nutshell how we prove that. So let me save the remaining time just discuss some further questions. I think, where does this lead next?
So the sum of squares proof degree depends on K?
Sum of squares proof, I'm not quite sure how to answer that, but the number of terms does not. Yeah, I mean, the uniformity goal gets larger and larger, right? But kind of the shape of the proof is constant for K. Okay, so in this paper of Bollobás, Brightwell, and Nieder, okay, so they proposed quite provocatively a theory of random K-sat functions, which that they're trying to study through this conjecture and through this work. So what does this mean, right? So it's what I talked about. If you take a random K-sat function, what does it look like? What are its properties? And in that vein, I want to propose a couple of directions, or at least mention a couple of directions in analogy to what we study for random graphs. So what we've done so far is counting K-sat formulas, which is like counting graphs or studying GN1/2. Of course, we now do a lot more than GN1/2. So there are a couple of natural directions to go further. One is, so the subsequent work of Bollobás and Brightwell, they conjectured that if you let K increase with N, and they conjecture that if K is at least or below half N and a little bit, then the number of K-sat functions is still asymptotically given by the same formula. Okay. Our techniques get nowhere close to this. We can let K increase maybe a tiny bit. I don't want to say anything on the record, but maybe log N or something like that. That's not on the record. But it's nowhere close to linear. Okay. Right, so then you can ask, well, what is a threshold in K for which the typicality structure still holds? Another direction is analogous to sparse random graphs. Here, there are several different ways to formulate this question. And one way, which I think is quite natural, is what is the typical structure of a minimal K-sat formula with M depending on N clauses? So what we study is a dense case where M is essentially on the order of N to the K. But like in random graphs, you can consider sparser formula. And then what happens? Again, this is different from the satisfiability of random formula problem, which is, well, that's really in the regime of taking a linear number of clauses and asking for satisfiability. Here, we're conditioning on already being minimal, and very few formulas are minimal, but condition on minimal, what is the typical structure?
So you asked for the typical structure, but do you know how many there are?
So yeah, the question is, what's the relationship between typical structure and how many there are? Well, if you can describe the typical structure, then it's usually pretty easy to write down a formula for the enumeration. So they're related to each other. Just like once you know it's unate, then it's pretty easy to count unate. Okay, that's all.
Any questions? I have a question about the statement that most triangle-free graphs are bipartite.
Do you know what edge density regime is that ruined? Because once you take like sparse enough graphs, it's not true.
Yeah, no, it's a great question, and this has been very well studied. I think the answer is around density 1/√n. This is something that's extremely well studied. And the container method is a modern perspective. That's a very powerful tool precisely for that kind of questions.
I think. Cool, thanks.
For those of us who haven't seen the use of sum of squares in this context, can you say a few words about that?
Oh, okay, so let me think about what I can say. Let me write down some version of the certificate, right? Without all the nitty-gritty, right? So there will be some statement which has this form. So I'm doing this not so that you can understand what I'm writing, but just to give you a shape of what such a sum of squares certificate might look like. So what does this mean? Here, okay, you can either view this as a formula in X is actually straight. Okay, so I have some graph. And I pick random vertices, x1 through xk minus 1, and then y and z. And I ask, what's the probability that that is an edge? What's the probability that this is a directed edge? Probability that this is not an edge, that is an edge, that's not an edge, that's a directed edge, and so on and so forth. And this is true. Okay, so this is true. And it is true because I can rewrite this formula as a sum of squares. I can rewrite a sum of squares. And then because this is true, okay, so and then you notice that this thing here. Let me take back the last thing I said. It is true because there are actually only finitely many cases to check. So it is true. And then you notice that whatever is in this red bracket is a square. A squared 2ab, b squared. That is a square. So that's non-negative. So I can just erase the whole thing and I get what I want. Is that okay?
So what was this finitely many things to check? So that part is not the sum of the square, or is
yeah, so there are k plus 1 vertices, yeah. And then there are only basically finitely many possible configurations of k plus 1 vertices. And then we can just case by case check that for every single configuration where the forbidden structure is enforced, this is true.
So you checked all of the cases by hand?
There are only really like 3 different cases.
So what were the previous proofs for k equal to 3 look like?
The previous, okay, great. What does a previous proof of k equals 3 look like? So here's the thing. Before using flag algebra, another approach is that if you know that the density, whatever this thing you're trying to do, is always true on 6 vertices or 5 vertices, then it is true for larger graphs as well by sampling. So you can just check all the configurations on 5 vertices. Now, that 5 gets pretty large as k goes up, so this method doesn't quite work exhaustively. It doesn't quite work computationally for larger values of k.
I have 2 questions.
Yep.
The first one is that generally extremal problems for directed graphs are hard. And a basic example is the Kata-Hagris conjecture about out-degree condition that would imply you have a directed triangle, such like a triangle and directed graph. And for hypergraphs, they're also hard. Like we don't know what the optimal density is for containing the uniform hypergraph. So the question is, what makes this more approachable than
So that's a great question. So I mean, we struggled with trying to solve this hypergraph Turing problem for a very long time. Right? And to this day, we still don't know, even for k equals to 3, what is the optimal constant there. And that's closer to the classical hypergraph Turing problem. But actually, in our work, we, especially in our earlier parts of our work, we took a lot of inspiration from the cases of hypergraph Turing problems that have been solved, including for a Fano plane. So actually that, I didn't know that before. So from density is known for the Fano plane, and there's some really nice techniques involved in that proof. And all of those things were quite useful.
So the second question is, I know one other example where the flag algebra approach, one actually learned information from that and then was able to generalize for general K, and that's the Ryer's quick density theorem. So this is the second example I'm aware of. Do you know other examples? It seems like a generally good idea for some general problem that you might see what's going on with all values of K, and then generalize it.
So you're asking for examples of flag algebra proofs, which is not numerical, but somehow works for infinitely many. Yeah, I don't know other examples. Oh, yeah. This with the Ryer's K clique, that is one that Jacob mentioned.
So when you tell this problem, did you start by trying k equals 4 first and k equals 5, or did you just, we're going to solve it for all k?
We tried small cases. We worked very hard.
Did you have like a proof that only worked for k equals 4 or k equals 5 at one point, or?
Right. So so we initially had, before the flag algebra proof, we had a proof which actually was quite nice for k equals to 4. There's some nice things about that proof too, but I won't get into it. And then so Nitya actually worked with a high school student at NYU and really brute forced the proof of k equals to 5 by a very massive computer search.
Like,
I don't think you can do more than k equals to 5 through brute force search.
I see, because I do remember at some point like 4 and 5 had been done, but not all k, and then that's you guys did all k.
For this computer search you did you try to force it somehow to spit out like small certificates or something, or it was just lucky that you did?
Okay, great. So the question is like, how do we get something which is quite nice? There was a lot of interactivity, right? So we really wanted a proof which is not just a proof, but have, let's say, rank 1 or there's few terms, so that we could eyeball it and figure out what's going on. And in fact, this proof, even strangely, only works for k at least 4. It doesn't work for smaller values of k. So all the numerics don't work out for smaller values of k. So in a way, we were also lucky that such a proof works in general.
But could you force that the rank is small for the certificate somehow, like when you did your computer search?
Yeah, so you should ask Bernard Lidický. He's an expert in actually doing computation with these flag algebra proofs. Yeah, that's a good question. But the question is, if you try to run SOS proofs on a computer,
it's not something random.
But can you kind of constrain the rank? I think maybe in practice there's some methods to try to force the rank to be nice.
Does that thing you wrote down actually correspond to a non-minimal formula? Did you say something about 2 globes?
Okay, so I said something very quickly. Right? So which is that these things don't correspond to a non-minimal, but if you have a formula that converts to this one, then the 2 blow up, that's going to cause you problems. The 2 blow up of that formula is going to contain any subformula will contain a contradiction.
What's the 2 blow up of a formula?
Yeah, so think about the 2 blow up of a graph, you double all the vertices. So 2 blow up of a formula, you double all the variables.
And they're truth decay times this. Okay.
All right, I guess just thank the speaker again and have other questions. Are you ready?